Okay, so what we're going to do today is start our discussions on periodic signals, right? So, I mean, what comes to mind immediately when you hear of the term periodic signal, right? What comes to mind?
Repeating.
Repeating, right? So, a periodic signal, like Munim said, is a signal that repeats itself, and that's why there's a sense of periodicity in that signal, and we're going to come across many periodic signals in this course, and for the prime example of that being, of course, sinusoids. Okay, so it's important to study periodic signals. Okay, so the formal definition, if I may, for continuous time signals is the following. We say that a continuous time signal is periodic if there exists, so let me use English here. So if there exists some capital T, which is a real number, right? So with some T, which is an element of the real set, such that x of t, the signal evaluated at some time t, small t, is equal to the signal evaluated at that small time t plus capital T, right? For any small t that I pick, if the signal repeats itself after capital T seconds, and if there exists some number capital T which satisfies this condition, then we say that the signal is periodic. Okay, is that clear? I mean, and that I mean, if you want to translate that sense of periodicity or repeatability into a mathematical equation, this is how you do it. This is how you will do it, right? So you just say, okay, the signal evaluated at any time t should be equal to the signal evaluated at that time t plus capital T. So there's a repetition after capital T seconds, right? Is that clear? Mathematically, this is how you'd formulate that repeatability, right? Periodicity, okay? And if this capital T that exists, we say that this capital T is for the time period. Okay, and one can easily show. Sorry, one can show that if x of t is equal to x of small t plus capital T for all t, then x of t must also be equal to x of t small t plus some small m times capital T for any m being an integer. So can somebody try to explain what this statement means? I mean, before I actually show that this is true. I mean, if x of small t is equal to x of small t plus capital T, that automatically implies that this condition must also be satisfied for any integer multiple of capital T as well. Okay, so G Hassan.
So this is just talking about because it's periodic,
Yeah.
you won't have it repeating just once. You can have it repeating as many times as possible. So m integers would just be plus a time period, plus a time period, plus a time period, and so on.
Right. So what the statement, so let's just look at the statement first. So the statement says that the signal repeats itself after capital T seconds. That means it must also repeat itself after 2 times capital T seconds, or 3 times capital T seconds, or 4 times capital T seconds, and so on and so forth. Okay. And I'll give you an example right after this, but let's just look at this mathematically first. Okay. So mathematically speaking, how do I prove this? I mean, anyone here venture a guess? I mean, how do I prove this?
Sinusoids.
Sinusoids,
Yes,
okay.
sir.
So, Munim, you raise an important point. Sinusoids, again, when I ask you to prove something, right, or when anybody asks you to prove something, I mean, it's not enough to take one example and show कि जी इस example के ऊपर ये चीज satisfied है, so this must hold in general as well. So that proof has to be general, it has to be generic, it does not have to be restricted only to sinusoids. Okay? So this has to be general. Okay? So anyone else? Apologies, Hassan. I want to say कि बाकी कोई बता सकते नहीं बता सकते. What do you think? I mean,
कहते हैं आपको जो है वो फ्लोर फंक्शन e t minus t फ्लोर फंक्शन जो भी है it's
yeah, but
periodic.
once again, that's a specific example. I want to remain generic.
Generic.
Right.
Sir,
So
general proof.
so here's how.
Music.
General. So if x mathematically, so if x of t is equal to x of small t plus capital T, and this holds true for any small t. So this holds true for any time from minus infinity to plus infinity, for any small t from minus infinity to plus infinity, right? So then if this condition is satisfied, right, then this must be true for time t plus capital T as well, right? So because small t plus capital T is still on the number line, is still from some number from minus infinity to plus infinity. So if this condition of this equation 1 holds true for small t, this equation 1 must hold true for small t plus capital T as well, because small t plus capital T is still on the number line. Okay? So if I plug the small t plus capital T in 1, right, what do I get? What I get is on the left-hand side, I get x of small t plus capital T. What do I get on the right-hand side? G. Roshin, what do I get on the right-hand side? Roshin, what do I get on the right-hand side? Are you there? Okay, Essen?
Sir, x of t plus 2t.
Good, right? So I just plug in, instead of small t, I have t plus capital T, and then there was a plus t there anyway, right? So therefore, this is x of t plus 2 times capital T, as Essen said. But from 1, I know that this is equal to x of t. From equation 1, right? And therefore, this must imply that this is equal to this thing here, right? So because there's an equality all over, right? So this must imply that x of small t is also equal to x of small t plus 2t, right? And then using induction, you can prove that, I mean, this must, if 2t is satisfied that, so you plug in t plus capital T once again, and you can show that this x of t must be equal to x of t plus 3t, and so on and so forth. Okay, so that's sort of an idea of a proof why this holds true. Okay, Ji Ahmed.
मैं पूछ रहा था कि उसके वजह से आप जो था कि फ्लोर फंक्शन में क्या होगा सिर्फ फ्लोर फंक्शन पावर सिग्नल या एनर्जी सिग्नल
So we're not talking about the floor function yet. I mean, floor function कहाँ से आ गया?
असाइनमेंट में आपका जो था वो समझ ही नहीं आया कैसे करना था
That's the assignment, right? So I mean, we're not talking about any particular problem. I'm just saying any periodic function, regardless of what form it takes, right? What form it
x plus
takes,
2t
whatever it is, x of t, if it's periodic and capital T is a period, then x of t must be equal to x of t plus m times capital T for any integer m. Okay? So what I'm saying here as a conclusion is this statement here, right? This statement here holds true for periodic signals. So if it repeats after capital T seconds, it must repeat after 2 times capital T seconds as well. Okay, now, or 3 times capital T seconds and so on and so forth. And just to illustrate this through an example of what I'm talking about, I mean, here's an example. This is an example of a periodic signal. Okay, on the x-axis you have time. On the y-axis you have the amplitude of the signal, right? So this is so on y-axis is x of t, right? So this is x of t, right? So what is the period for this signal that you see on your screen?
Periodic signal.
Okay, so Munim says the period is 2, and that's correct. Why is it 2? Because you can clearly see that every 2 seconds this period the signal repeats itself, right? So if I say, yeah, this is 1 period, right? And then this is another period, and clearly, and this is another, so this is the first period, the second. Clearly what I can see is every 2 seconds there's a repetition, right? Every 2 seconds there's a repetition, and I can say that the period is capital 2. Oh, sorry, period is 2 seconds, right? Ji Hamza.
जी सर, मैंने ये पूछना है कि आपने ये स्पेसिफिक एग्जांपल दिया हमें एक पीरियोडिक सिग्नल की। सर अब मैं इसको अगर 1 यूनिट पीछे से लिंक करूं तो सर क्या ये पर्टिकुलर सिग्नल एक इवन सिग्नल है हमारा?
So because I am not exactly showing you on the left hand side, but because it's periodic, so yes, it will be an even signal. I mean, if you extend this on this negative side, मैं आपको दिखा नहीं रहा, असल में extend कर रहा हूं, of course.
ठीक है।
Right, so yes, it will be an even signal. Good.
All right, thank you sir.
Ahmed, do you still have a question? Your hand is raised. All right, thank you. All right, so the period is from this is 2 seconds. But I then say, yeah, 2 seconds के अलावा 4 seconds भी period है. I mean, does that make sense? And the 4 seconds is also a period. How can somebody? So
Because every 4 seconds the same is repeating.
So it's also repeating
repeating.
4 seconds. Good, Ahmed. Anyone else who would venture an explanation? Manur? Right. Okay, Hassan, go ahead.
So it is definitely, you can count that as the period as well, because what it consists of is basically 2 time periods. So if I call 0 to 2 seconds 1 unit,
Yeah.
then 0 to 4 seconds is just 2 units of that same repeating pattern.
Excellent. Right. So I can see, I mean, immediately as I look through this graph here, right, I see कि यार वो 2 seconds वाला भी था, but then this is also true. I mean, if I just do this demarcations, right, and then I also see कि यार the signal over here is the same as a signal over here, is the same as a signal over here. So now there's a repetition after 4 seconds as well, right? And which basically illustrates the point through an example, the mathematical point that I showed just earlier. If capital T is a period, 2 times capital T must also be a period, right? So therefore, if in here, 2 seconds is a period, so therefore 4 seconds must also be a period. And similarly, 6 seconds, by the way, must also be a period as well. I mean, does that make sense? 6 seconds must also be a period as well. So if I just collect 3 smallest periods together and I say that iske baad ye repeat hona shuru ho gaya, so that would still hold true, and 6 seconds would also be a period. Okay, so through this illustration that you see on your screen, I mean, this just drives home the point, or an illustration of what this equation that you see in your box represents. Okay, if capital T is a period, m times capital T must also be a period. Okay, is that clear? All right. But then if अगर 2 seconds भी period है, 4 seconds भी period है, 6 seconds भी period है, so there must be just one period which characterizes the periodicity, right? And that is a term we use which is called the fundamental period. Okay. All right. So here's a definition. is the fundamental period? So anybody wants to venture a guess? Okay, what do you think the fundamental period is going to be?
So it's the smallest repeating unit.
Is the smallest repeating unit. But in terms of this language that we've defined, Musa, right? In terms of this language that we've defined, can you try to link what you just said with the language that we define up above?
Not sure which terms exactly you mean.
So I mean KG.
Okay. It would be the fundamental period would be plus t, I guess. Every capital T it repeats. So
okay. So here's what the fundamental period is. So I know KG, there could be multiple periods of a periodic signal. Okay, if 2 is a period, so 4 must also be a period. Or in other words, if 4 is a period, then 8 must also be a period, because every integer multiple of that period is also a period, right? But the fundamental period is defined as the smallest value, smallest capital T, being an element of R plus. What is meant by R plus?
positive real values.
Positive real values. So by definition, the fundamental period is defined as a positive real number. Okay, so that's a definition we make. It does not have to be like in the definition हमने बना दी है क्योंकि so that's a rule that we stick by, right? So it's defined as the smallest positive real number which satisfies what x of t equal x of small t plus capital T for all t, right? That's the fundamental. Okay, G Ahmed.
I said T.
Yeah.
Smallest T just said was T.
Okay. So now coming back to this example. What do you think is the green curve that you see? What do you think is the fundamental period here? So we know 2 is a period, 4 is a period, 6 is a period, 8 is a period, and so on and so forth. What do you think is the fundamental period for this periodic signal?
It could be 2.
It would be 2. Okay, so here the fundamental period is 2. Can it be 1?
No, because from 0 to 1,
fundamental period is
the
not
same
1.
pattern isn't.
Okay, so 2 is the smallest number that satisfies that periodic condition, x of t equals x of t plus capital T. Because the smallest capital T which satisfies that is capital T equals 2. Right, so 2 is a fundamental period, but because 2 is a fundamental period, we know any integer multiples of the fundamental period are also periods of this signal, okay, of this periodic signal. Okay. So let's do an example for a sinusoid, and then we're going to build on top of it. And I mean, this is a signal that you must all be familiar with. It's just a sinusoid. And that's probably the simplest signal that comes to mind when you think about periodic signals. And so this is x of t equals a times cosine omega naught t plus phi. And I wish to determine what the fundamental period is, right? In order for me to determine the fundamental period, what I would do is I would see, let me evaluate x of t plus capital T. And I see that this is equal to a times cosine, and the function evaluated instead of at t, but evaluated at t plus capital T, it would be omega naught times t plus capital T plus phi, and therefore this is a times cosine omega naught small t plus omega naught capital T plus phi, right? And the question then is there a value of capital T which ensures that x of t plus capital T turns out to be x of t, right? So a times cosine omega naught t plus phi plus omega naught t turns out to be equal to A times cosine omega naught t plus phi for what value of capital T? So, okay, so here's one. So for all t, when what condition is satisfied? I mean, what should this be equal to? What should this be equal to for this equality to be satisfied? Ji Hamza?
Sir, omega naught capital T should be equal to 0. It was
Okay, so that's one way of saying this. The omega naught capital T must be equal to 0 for the left hand side to be equal to the right hand side. But then that's not really saying anything here. Why? Because when you're saying omega naught capital T equals 0, what you're saying is capital T equals 0, right? But then capital T equals 0 just means that you're just talking about the signal itself. You're not added anything in the time axis. So capital T equals 0 just means this x of t is equal to small x of t. That's nothing there. So you need to find a positive capital T. Okay? Ji Musa.
So what if it's like n2 pi?
Okay, excellent, right? So there has to be a 2 pi or an integer multiple of 2 pi. But the smallest value that satisfies that condition is 2 pi. I know that 2 pi ke alawa 4 pi bhi hogi, 8 pi bhi hogi, 6 pi bhi hogi, minus 2 pi bhi hogi, by the way, right? But the smallest value of capital T, which ensures that the left-hand side is equal to the right-hand side, is when omega naught capital T equals 2 pi. Okay, so the fundamental period is what? That we can find that to be T equals 2 pi over omega naught. Okay, that's the fundamental period, and provided omega naught is positive. If omega naught is negative, the period just have to multiply this with a minus sign. Okay, and this makes sense. I mean, so you know, it's a sinusoid. Sinusoid ki frequency kya hoti hai, right? So omega naught is the frequency, which is radians per second, the number of revolutions, the number of it completes omega naught radians per second, right? And I know that one revolution is 2 pi radians, right? So the number of revolutions that you're going to complete in 1 second is going to be equal to omega naught by 2 pi, and therefore the time period is going to be the inverse of that, which is 2 pi by omega naught. I mean, all high school things that you've done. Okay, it's just that we're now framing this in the in this language of periodicity and the fundamental period and capital T and so on and so forth. Okay, so this is the fundamental period, which is capital T equals 2 pi by omega naught seconds. Okay, and of course omega naught is the frequency in radians per second. Okay, all right. Here's a question for you there. So another example. If I say here, there's a signal x of t, which is equal to the following signal: cosine 2 pi t for t is greater than or equal to 0, and a 0 for t is less than 0. Is this signal periodic? And if it is periodic, determine the fundamental period. So who thinks the signal is not periodic? It's a cosine, right? So it's is this a signal? Is this signal not periodic? So who thinks the signal is not periodic? No one. So everybody thinks this is a periodic signal. Okay, so Musa, can you unmute yourself? You say okay, it's periodic within a certain range. Okay,
Yes,
what do you mean by that?
according to the piecewise function you defined. So
Okay.
it's not periodic if it's less than 0, t is less than 0. Otherwise, it is for
Right.
all
Right.
positive values.
So let me make a point of clarification here that the periodicity is a function, is a property of a signal, and where it's not a function of ranges. Okay. So as far as this definition was concerned, I mean, as this definition 1 was concerned, this needs to be satisfied for all t, right? For all t, belonging to the real set. I mean, I cannot say कि यार ये थोड़े के लिए satisfy होनी चाहिए तो फिर भी मैं कहूँगा periodic है, right? So this must be satisfied for all time instances for the signal to be called a periodic signal, right? So clearly from what you're saying is this condition is satisfied for t is greater than 0, but it's not satisfied, or you think it's satisfied for some values of t, but it's not satisfied for other values of t. Again, if there's even a single value of small t for which this condition is not satisfied, then we'll say that the signal is not periodic. Okay, because it does not infinitely repeat itself. Okay, is that clear? So therefore, this signal is not periodic, because if I were to sketch this signal out, I mean, this is what the signal is going to look like. I mean, this signal is going to be 0 for all time less than 0, and then it's a cosine, so it goes up, so there is continuity there. So, and this is what the signal looks like. And clearly, this signal is not periodic. Why? Because this value, even though it's the same value as this, but over here, this is not the same value as यहाँ तो 0 था, is not equal to 1, right? So therefore, this signal is not periodic. So no is the answer. All right. So let me just up the game a little bit and talk about another example. So this is a slightly more involved example. Right. So if I say, chalo, choti example. So x1 of t is cosine pi t, right? Is this periodic? Of course it's periodic. What is the period for this? So what is the period for x1 of t?
I think it's pi.
It is what? Pi?
Pi. Yeah.
Right. So remember, this is 2 pi by omega naught, right?
Yes. So 2 pi divided by pi is. Oh, sorry, I meant to say 2.
Yeah, 2. So 2 pi by
वही
pi.
मैंने division गलत कर दी थी. Yeah.
Right. So this is 2 seconds. Okay. So the signal repeats itself after 2 seconds. Let me give you another signal, x2 of t, which is cosine 2 pi t. Right. So the frequency is doubled. If the frequency is doubled, what do you expect for the time period? What should happen there? The time period should half, right? So, and you can clearly see that this is 2 pi by omega naught, but omega naught is 2 pi, and therefore this must be 1 second, right? So x1 of t is periodic with 2 seconds, x2 of t is periodic with 1 second, with a fundamental period of 1 second, right? Now here's a question. So if x of t, I define another signal x of t, which is actually equal to the sum of x1 of t plus or 2 times x2 of t. Okay. Is this signal periodic? And if it is periodic, if it is not periodic, explain your reasoning. And if it is periodic, determine the periodic, the fundamental period. So what do you think? So Mustafa Siddiqui. Mustafa? I just want to figure out, Katie, I mean, are you guys really here? Mustafa, are you here?
अस्सलामुअलैकुम सर, माइक का मसला था, दोबारा रिपीट कर देंगे मेरे इंटरनेट कनेक्शन का सवाल.
Right. So is this signal that you see on your screen, is this periodic? Why or why not? Okay, Ibrahim, you have answer?
जी सर, आई थिंक इट्स नॉट पीरियोडिक, क्योंकि 2x2 करने से सिर्फ उसका एम्पलीट्यूड हम वो एम्पलीफाई कर रहे हैं, उसके अलावा तो और कुछ नहीं कर रहे. उसका टाइम पीरियड तो x2 वाले का सेम रहेगा.
Okay, so I mean, my question is the sum periodic? I mean, so what I'm saying is x of t periodic? Chale, is x of t periodic? So Ibrahim, your answer is it's not periodic. Is that what you said?
Yes, sir.
Okay, and your reasoning is because you're multiplying by 2.
Yes, sir. जैसे x1 of t का तो मैक्सिमम एम्पलीट्यूड हमेशा 1 ही जाएगा ना,
Yeah,
मगर x2 को हम से मल्टीप्लाई कर रहे हैं तो वो तो 2 और -2 के दरमियान नहीं कर रहा होगा ऑसिलेटर।
बिल्कुल होगा, लेकिन
That
how
should-
does that affect periodicity? I mean, how is that related to periodicity?
सर वो भी आपने ऊपर बताया ना कि जैसे उसकी वैल्यू फंक्शन की 1 थी अभी, तो
Yeah.
पीछे वो 0 हो गई थी एक टाइम पीरियड के बाद।
वैल्यू 1
तो
नहीं है, फंक्शन की वैल्यू 1 नहीं है, फंक्शन तो फंक्शन है, उसका फंडामेंटल पीरियड 1 सेकंड है, right? So here's a depiction of what the signals are, right? So these are what the signals are. Right? So Ibrahim, the signal that you see
sir.
in red is cosine pi t. The signal that you see in blue, dashed blue, is 2 times cosine 2 pi t. Okay? Clearly x1 of t is periodic. And what is the period for x1 of t? The period for x1 of t is, as we found out as well, is 2 seconds. Right? So, I mean, clearly यहाँ से start होता है ये red signal, ठीक है? और वापस peak दोबारा से 2 seconds पे आती है. So the period is 2 seconds. Okay, fundamental period is 2 seconds. But what about the period of blue?
सर ब्लू का 1 सेकंड
1 second है, but लेकिन 1 second अगर period है तो as we did before this as well, is
fundamental period is 2.
the period is 2 seconds as well. अगर 1 second period तो 2 second भी period होगा.
Fundamental period is 2. Fundamental period is 2.
Good. So let me hear other people. Hamza, you want to say something?
Yes, sir. I just wanted to answer the question. I think that this function, the function x of t after adding x1 and x2 will be periodic, and the period would be the higher period amongst the two given functions, which is 2 in this scenario.
Why is that, Hamza?
सर क्योंकि अगर सर थोड़ी सी इंट्यूटिव रीजनिंग ही थी, जैसे अभी ग्राफ मेरे सामने है तो बेसिकली इट विल जैसे ही आप उनकी वैल्यूज सुपरपोजिशन की वजह से जब आप इनकी वैल्यूज ऐड करते हैं, सो आफ्टर अ पीरियड ऑफ 2 seconds उसकी वैल्यू रिपीट होगी. दैट इज लाइक व्हाट आई थॉट.
Okay, so you're sort of yes, you're right कि 2 seconds बाद red signal भी repeat कर रहे हैं और 2 seconds बाद blue signals भी repeat कर रहे हैं, ठीक है?
जी
दोनों का sum भी इसका मतलब 2 seconds बाद repeat करना चाहिए. So that's an intuitive reason. Hassan, go ahead.
सर मैं बस ये कहना चाह रहा था कि as we just saw just अभी कि we have a fundamental time period,
Yeah.
but then we also have periods after that. तो हमारे पास अभी 2 फंक्शन है.
Yeah.
एक का पीरियड 2 सेकंड है, एक का 1 है.
Yeah.
बट जिसका 1 सेकंड है
Yeah.
उसका 2 सेकंड भी पीरियड है, क्योंकि we can just add 2 fundamental blocks.
Good.
Which is why both of them together will also form a periodic function जिसका 2 second overall होगा.
Excellent. So I want to listen to Mustafa as well. Mustafa Siddiqui, you said something in the chat box. I mean, you have the right answer. Can you try to explain your reasoning?
सर मैंने टाइप मेरा अचानक अभी क्या कहते हैं डिस्कनेक्ट हुआ था.
Okay.
मैंने टाइप किया था कि यही चीज जो अभी बोल रहा था
Right. ठीक है, good.
कि 2 seconds बाद दोबारा रिपीट होगा.
Ehsan and Hamza, अगर you want to say something similar or do you have some different reasoning? Hamza?
सर मुझे बस ये समझ नहीं आई थी कि इक्वेशन से हमें किस तरह पता लग रहा है कि ये दोनों ये x1 of t और x2 of t का सम periodic होगा.
So I'll come to the equation in just a bit. I mean, I want to illustrate this first and then go back to the equation. Okay? So I'll build that connection in just a bit. Ehsan, आपका question है? Do you have an answer या फिर?
मेरा क्वेश्चन है कि अगर दोनों फंक्शंस का जो पीरियड्स है मल्टीपल्स उनके इक्वल नहीं होते किसी भी पॉइंट पर, तो फिर उनके जो सुपरपोजिशन है उसका पीरियड क्या होगा?
So okay, I'll come to this point as well. But let's just look at this particular example and then we'll move forward. Okay? So for this example, you see, which is the green, the signal that you see is actually the sum. As the green signal that you see is actually the sum. And clearly, when you see the green signal, you see that the green signal is indeed periodic with a period of 2, right? And the intuitive reasoning, once again, is because of the fact that as many of your colleagues mentioned already, that the red signal has a period of 2 seconds, and the blue signal has a fundamental period of 1 second. But since 1 is a fundamental period, 2 must also be a period. तो दोनों का जो common period है वो 2 seconds है, and therefore the superposition must also be periodic with a period of 2 seconds, as you can see in the this is a visual confirmation of what that intuition is. Now let's go back to the equations here, right, and see why this must be true. Okay, so this is the equation, right, and what I do here is, okay, let me do this. So what is x of t plus 2? What is that equal to? I see that I just plug this into the sum. This is x1 of t plus 2 and 2 times x2 of t plus 2. Right? Is that clear, Hamza? All I've done is, let me just try to evaluate the signal at time t plus 2 seconds. Okay? And then what I observe is that x1 का period क्या था? x1 का period 2 seconds था. So this, therefore, what is this equal to? So what is this equal to, Hamza? If 2 is a period of x1, what is x1 of t plus 2?
सर पीरियड सेम नहीं रहेगा?
हाँ, पीरियड सेम रहेगा, लेकिन x1 of t क्या होगा?
सर वही रहना चाहिए, सिर्फ वो आगे शिफ्ट हो रहा है ना?
हाँ, वही रहना चाहिए, right? So वही रहना चाहिए, लेकिन what is x1 of t plus 2? I mean, if 2 is a period, so it must be x1 of t, as Ibrahim said. If 2 is a period, so therefore this must be x1 of t, because it's going to repeat itself after 2 seconds. Right? And what about this? What about this signal here?
सर ये भी फिर x2 of t रहेगा.
Okay, x2 of t क्यों रहेगा? लेकिन remember x2 का fundamental period 1 था, right? But I know कि 2 भी period है. Therefore, this must also be, because 2 is also a period, this must be x2 of t. And therefore, from this I conclude that this must be equal to x1 of t plus 2 times x2 of t, but this is x of t, right? So thus what we know is, this implies that x of t plus 2 is equal to x of t, right? And this is true for all t, and therefore this implies that the period of x of t is 2, right? Okay, Hassan, I'm going to come to this point that you raised in the chat box, and there were some other people who raised the same sort of similar point as well. Okay, let me up the game a little bit even more, right? So here's another example. So once again, we're dealing with sinusoids, and x1 of t is so x1 of t is cosine pi by 3t. So what is the period for this? Period is, of course, 2 pi by omega naught, right? And 2 pi by omega naught, if I just plug in omega naught, this is 2 pi divided by pi by 3, so this is 6 seconds, right? And then let's consider another signal, x2 of t, which is sine pi by 2t, right? And the period for this is what? 2 pi by omega naught. And this is 2 pi divided by pi by 2. And this is 4 seconds. Okay. So one of them has a period of 6 seconds. The other one has a period of 4 seconds. If I form a new signal x of t, which is equal to x1 of t plus x2 of t, right? What is the period? I'm telling you this is going to be periodic. Okay. And I ask you, okay, what is the period for this? So somebody other than Hassan, can you try to guess? Ji, Ibrahim, Mustafa, excellent. Ibrahim, can you explain your reasoning, please?
सर वो T1 का फंडामेंटल टाइम इज 6 और T2 का इज 4.
Yeah.
तो 6 उनका लीस्ट कॉमन मल्टीपल वो 12 आता है.
12 आता है. So what you're showing is कि जी, because 6 is a fundamental period of x1, तो and 4 is a fundamental period of x2, so we just need to find a common multiple, right? A common period. So 12 is that smallest number, which is a period of x1 as well as of x2. Okay, and therefore must be a period of the sum as well. Okay, so that's clearly right. So that we can see that the x of t plus 12 equals x1 of t plus 12 plus x2 of t plus 12, and this is indeed x of t. I'm skipping steps here. So the answer to this question is 12. Okay. Now, the following is an exercise. I'm not going to give you the solution here. So I give you x of t is equal to cosine pi t plus sine 3t, right? And the question is x of t periodic? If yes, determine period. And this is an exercise. Let's not have that discussion here. We can have it sometime later. Okay. All right. Any questions about what we've done so far? जी इब्राहिम.
जी सर, मैं ये कह रहा था कि जैसे जो ऊपर वाली एग्जांपल हमने की तो इसके अंदर x1 of t plus 2x2 of t या मतलब कि किसी से हम मल्टीप्लाई कर दें किसी भी फंक्शन को तो उससे कोई फर्क नहीं पड़ता, राइट?
फर्क नहीं पड़ता. Why? Because if x2 of t is periodic with a period of 2 or whatever that period is, 2 times करने से उसको सिर्फ स्केल करने से उसके पीरियड पे कोई फर्क पड़ता नहीं पड़ता. Of course not.
जी ठीक है सर.
उसको शिफ्टिंग करने से भी पीरियड पे फर्क पड़ता ही नहीं पड़ता.
सर पढ़ना तो नहीं चाहिए, आई थिंक.
नहीं पड़ता, बिकॉज अगर आप शिफ्ट करेंगे तो तब भी दैट कंडीशन इज सैटिस्फाइड, राइट? व्हाट अबाउट
जी सर.
कंप्रेस इट और एक्सपैंड इट?
सर तब तो पड़ता है फर्क पीरियड पे, उसका पीरियड कम ज्यादा होता है.
एग्जैक्टली, तब पढ़ना चाहिए. कोसाइन को आप सो कोसाइन की जिसकी फ्रीक्वेंसी कुछ थी उसको आप कंप्रेस करेंगे तो फ्रीक्वेंसी ज्यादा होगी कम होगी?
सर कंप्रेस कर देंगे तो कम हो जाएगी फ्रीक्वेंसी, और फ्रीक्वेंसी ज्यादा हो
जाएगी
पीरियड,
राइट? एंड एक्सपैंड करूंगा तो फ्रीक्वेंसी कम हो जाएगी. ठीक है. एंड दिस यू कैन वेरीफाई फ्रॉम जस्ट मैथमेटिकली एज वेल कि इफ x of t is cosine omega naught t, right, then x of at is cosine a times omega naught t. So the new frequency becomes a times omega naught. So if a is greater than 1, so the frequency increases. If a is less than 1, the frequency decreases. And a is greater than 1 corresponds to compression. A is less than 1 corresponds to expansion. Okay? And this is one of the reasons, as you'll see on the demo. So this is an answer to the question that I have LMS tab से पढ़ा हुआ है, demos पढ़े हुए कि अगर मैं ऑडियो सिग्नल को कंप्रेस कर दूं तो पिच बढ़ जाती है, फ्रीक्वेंसी बढ़ जाती है. Okay, so we'll talk about this more as well in detail. But there's a demo there on the LMS tab. Just it will be interesting to look at it, to hear it and see what happens with audio when you compress it or expand it. Okay. Right. Any other questions? All right. So what we want to do next is talk about a particular class of signals, which is exponential signals and sinusoidal signals. So sinusoidal signals is more or less something we've already done. So let me just write this out here, not talk about that in a lot of detail. Sinusoidal signals. And those are, if x of t, the general form of a sinusoidal signal is here, is a cosine omega naught t plus phi. And of course, this is periodic, right? So there's a sinusoid, and the fundamental period is what? The fundamental period is 2 pi by absolute of omega naught. Why is this an absolute of omega naught here? I mean, why do I have an absolute? I mean, can somebody explain why? जी दानियाल, क्या ख्याल है? Okay, good. Right, so Ibrahim has the right answer because the period by definition, the fundamental period by definition, cannot be negative. And cosine, you know, can have a positive frequency as well as a negative frequency. Okay? And I'll have something more to say about this in just a bit. Okay? Negative frequencies ka matlab kya hota hai? Okay? So this is the fundamental period. So this is the fundamental period. All right. So what I want to spend more time on is our exponential signals. So actually, so let me start with real exponential signals. That is something that you must be familiar with. And I'll rather do this quickly. So x of t is equal to c times, let me forget about the c as well, e raised to power alpha t, right? Where alpha is real. So if I ask you to sketch this signaling, what would it look like? So what would this look like? Who should I pick on? Right, Umar Abdul Jalil. Umar, are you there?
Yes, sir. Sir, it could be an exponentially growing function.
Would be exponentially growing? Will this always be exponentially growing?
Sir, 0 पे 1 होगा.
Yeah.
और उसके बाद exponentially growing. और negative side पे जो है वो 0 को approach करेगा.
Okay. Umar is saying as the following. What Umar is saying is, okay, this is what the signal is going to look like. 0 पे 1 होगा. Okay. Anybody cares to disagree?
Sir, alpha की value पे depend नहीं करता.
Right. Excellent. So it depends on what alpha is. So this particular plot that you see on your screen, what value of alpha would this depiction correspond to? Before what values of alpha would this be a growing exponential? So this would be positive values of alpha. So this is alpha is greater than 0. Okay. On the other hand, if alpha is less than 0, that's when you have a decaying exponential. Okay. So this is a decaying exponential. And it goes to 0 as t goes to infinity. Okay. Right. So pretty straightforward, right? Then we have something called periodic complex exponential signals. And the general form of these signals, and these are the most fundamental of signals that we can think of. And the reason why I say this, these are the most fundamental of signals out there, is because all other signals that we come across in the world, in the universe, almost all of them, can be broken down into a superposition of these periodic complex exponentials. Okay, that's why they're so basic. That's why they're so important, right? And the general form of these periodic complex exponential signals in the continuous time domain is x of t being equal to e raised to power j omega naught t, right? So this is the most fundamental or the basic signal that you can think of in the universe, right? What does this signal look like? I mean, if I were to plot this signal, what would this signal look like? I mean, is this a growing exponential? Is this a decaying exponential, or is it something else? Right, G. Daniel, can you unmute yourself? Your periodic sine and cosine. So what do you mean by that? Daniel, are you there? Okay, anybody else? So it's you just apply Euler's identity here, right? So Euler's identity is e by j theta is cosine theta plus j times sine theta. So therefore, this must be cosine omega naught t plus j times sine omega naught t. So therefore, this actually is a complex signal, right? This therefore is a complex signal. So there is a real part of it and there's an imaginary part of it. And clearly, as you see, you can see the real part is a cosine and the imaginary part is a sine, right? And the omega naught is a frequency. If you increase the frequency, the real part oscillates with a higher frequency, much, much faster, right? And this the imaginary part also oscillates much, much faster, except that the real part and the imaginary part are 90 degrees out of phase, right? And sine, sine is 90 degree out of phase of a cosine. Okay, so that's what a complex exponential is. If I were to plot this in the in 3 dimensions, before I do that, let's try to visualize what this is going to be in 2 dimensions if I collapse it in 2 dimensions. So let's say this is the real part of x of t, this dimension, and this is the imaginary part of x of t, right? What happens at t equals 0? Where is the signal at time t equals 0 in this 2-dimensional complex plane? What happens at t equals 0? T equals 0 pe kahan hai signal? I mean, remember, complex number is only a vector in a 2-dimensional plane. Okay, with the real part is the x-axis, the imaginary part is the y-axis. Where is the signal at time t equals 0? G. Musa, what do you think? Right?
सर आप मेरे से पूछें?
हाँ जी, मूसा, 2 मूसा थे वैसे, चलिए आप जो
हाँ जी वही ना। मैं बताऊं?
Yeah, please go ahead.
Real axis पे 1 पे होगा.
Real axis. So Musa, just stay with me. And if I as I increase time, what happens? If omega naught is positive, let's assume omega naught is positive.
Okay, as you increase time, the value of cos goes down, and sine increases. That's why the real part it'll go like the circle will move towards the left.
Exactly.
And imaginary part will increase and.
Right, so you have a circle, right? So as time t moves, okay, what you're going to observe your signal to be doing is moving along a circle in this 2-dimensional plane with a frequency, with the speed which corresponds to omega naught. Omega naught zyada hai, so it's going to move faster. Omega naught kam hai, so it's going to move slower. Okay, but it moves on a circle. Okay, as time progresses, If omega naught was negative, it would have moved the other way around, right? In a clockwise direction. If omega naught is positive, it moves in an anti-clockwise direction. Okay. Now, how do you visualize this signal in a three-dimensional space? Right, so I'll show you some demos here that we made. But any ideas before I start doing that? I mean, what is this signal going to look like in a three-dimensional space?
Excuse me, sir.
जी.
सर ये एक helix की तरह होगा, depending on time की value क्या होगी, inward spiral या outward spiral.
Yes, it's going to be sort of yes, it's going to be a spiral, right? So, I mean, how do you come about this conclusion?
सर बेसिकली आपके पास साइन और कॉस की वैल्यू, जब टाइम की वैल्यू चेंज करते हो तो इट विल मूव अलोंग द सर्कल, लेकिन टाइम की कौन सी वैल्यू है वो कॉस और साइन को किस तरह अफेक्ट करती है उसके ऊपर डिपेंडिंग ये इनवर्ट भी हो सकता है, आउटवर्ट भी हो सकता है, तो दैट वाज जस्ट अ गेस.
Right, so you see in two dimensions it's moving around a circle. Like in time axis, time axis is inside your, or it's coming out of your screen. So as time progresses, this is what the movement in a circle is. So that circle movement along the time axis, is तरह move कर रहा है, and I'll show you an example or an animation for that as well. Okay, so you're right. This is going to be a spiral. Okay. Now I wonder if you can see both of my screens. Can you?
No, sir.
No?
I mean, we can only see your notes.
Okay. So let me stop this share. How about now?
Now it's desktop, I think.
Okay, desktop. All right. पहले desktop नजर आ रहा था नहीं आ रहा था. I was just trying multiple sharing at the same time.
नहीं पहले नहीं नजर आता, पहले सिर्फ नोट्स नजर आता.
Okay. Okay. So let me open up. Okay. Give me just 1 minute. So this is what the spiral is. This is what the spiral looks like for omega naught equals 4 pi. Okay. And as you can see, this axis is the time axis, right? And this axis that you see, this is the imaginary axis. This is the real axis, right? And it's clearly a sinusoid, is a spiral. And I can move this around, and I'll share this demo on LMS as well. If I can move this around to see what the projections are going to be on each one of the axes. Okay. So if I project the spiral on the imaginary axis, what does it look like? This is what it looks like. So let me pull this up, and you see, so I'm now projecting it on the imaginary axis, and it's clearly it's a sine wave, right? So there you go. Okay, so this is the time axis here, and this is the imaginary axis. And on the imaginary axis, this complex signal is a sinusoid. What about the real axis? So let me restore the view. Here's how. So I'm ऊपर से देख रहा हूँ. So I'm looking at the spiral from the top. Before this, I was looking at the spiral from the right. So this is what I see from the top, right? And this is the real axis, and it's clearly it's a cosine wave now. Okay, with the frequency which is accurately equal to 4 pi. Okay, and 4 pi corresponds to a period of what? It actually corresponds to a period of half a second. It's clearly half a second. This is where the period. This is what the period is. Okay. I can also look at it from here, and clearly it's a So what I'm doing is time axis ko collapse karke, I'm just looking at the imaginary axis and the real axis. And this is what it looks like, which is clearly a circle. Okay. So you can, so I'll share this demo. You can view this on your own PCs, rotate this around to see different dimensions of it. Okay. What I want to show you next is a simple animation, if you will, of how this spiral moves, right? So, right. So this just shows that the time t improve increase kare, and what does the spiral behave like, right? So it's a circle. It's circles moving around along the time axis, right? So as time increases, this moves along the time axis in a circular fashion. Okay. So this is what the spiral is. And if I increase the frequency, what would you expect? So what would you expect if you increase the frequency? So I mean, so there's a certain frequency here. Agar main frequency बढ़ा दूं, तो what would the spiral look like? I mean, what do you think? Anyone? Hamza, Rashid, I mean, what do you think? If I increase the frequency, what would happen to this spiral?
So the spirals would be closer together.
So it's going to be like compressing the spring. Okay, that's what the increasing the frequency means, right?
Yes.
So I can quickly increase this to 12 pi, right? And the frequency is 12 pi now. And this is what the spiral looks like now, right? So it's much, much closer. Right? So the frequency is increased, so that means it's packed closer together. The time period decreases. Okay? Right. Okay. So let me go back to my notes. And are they? Okay, I'm sorry, I was not looking at the chat window. Right. Okay, so I will share this on LMS. So there's a question, can we change the diameter of the spiral? So that's a good question. How would you change the diameter of this spiral, Daniel? What do you think? I mean, before I provide you with the answer, aapke kya khayal hai? Daniel, are you there? No idea. Okay. So scaling, okay, Ibrahim says scaling. So if I just multiply this, Daniel, with some number. So for example, I multiply this by 2, and you can do this with MATLAB code that I'm going to share you, right? You just multiply by 2. What happens is that the point is going to be moving along a circle which does not have a radius of 1 anymore, but rather a radius of 2. That's like increasing the width of the spiral. Okay? And the time, playing with the time axis increases the frequency or decreases the frequency. And then you can say, agar main phase add kar dun, to phir kya hoga? I mean, what if this was plus phi? And all of these ideas, you should go home when you go, you're already home. So when the class is over, when you're studying, so think about these something. What would happen if I add a phi, right? If I do something else, right? And so on and so forth. Okay. Now here's the point. Is this signal periodic? Right? Is this signal periodic, Daniel? And I mean, you could have seen from the graphs as well. Of course, this is periodic, right? I mean, you would have seen this is periodic. And the reason why it's periodic is because there's a cosine and there's a sine. And I know that cosine is periodic. I know that sine is a periodic as well. Okay. So another way to think to show that this is periodic is I just evaluate what x of t plus capital T is. In other words, I want to find a capital T which satisfies this condition that x of t plus capital T must be equal to x of t. So therefore, this is e raised to power j omega naught. Okay, so e raised to power j omega naught t plus capital T. This must be equal to e raised to power j omega naught t, right? So therefore, this is e raised to power j omega naught t times e raised to power j omega naught capital T. This must be equal to e raised by j omega naught T, and this must imply that the capital T, which would ensure that this condition is satisfied, must satisfy e raised by j omega naught T being equal to 1. What is a capital T that satisfies this condition? I mean, when is this true? I mean, don't say capital T equals 0. I mean, that's a trivial solution, right? This holds true.
2 pi.
Not exactly 2 pi.
Half pi.
No. This true.
Pi. T is equal to pi.
Right. So that's not T equals pi. Anybody else? I mean, it has to be a function of frequency. Right? This holds true when omega naught capital T is equal to 2 pi. Right? So that means this is periodic with a period of 2 pi. And with the fundamental period, I will put in the absolute value just to make sure that the fundamental period turns out to be positive. Right? So therefore, the conclusion is that x of t is equal to e raised by j omega naught t is periodic with fundamental period of capital P, capital T equals 2 pi by absolute omega naught, right? So that's why I said it's a periodic complex exponential. So this is a complex signal, but it's periodic. Okay? All right. Right, let me now try to compute the energy So what do you think the energy in e raised by j omega naught t would be? Any answers here? What is the energy? So energy is, and you may have done this in the homework. So this is x of t absolute squared dt. What is the absolute value of e raised by j omega naught t? That's just 1. And therefore this is infinity. So this is not an energy signal. But what about the power here? So power की definition क्या है? The power is limit t going to infinity 1 upon 2t integral from minus t to plus t x of t absolute squared dt. But therefore this is limit t going to infinity 1 upon 2t minus t to plus t. But the absolute value of x of t is just 1. And therefore this is just equal to 1. So I'm skipping a step. It's very, very simple. Okay, the integral is equal to 2t. 2t divided by 2t is 1. And therefore the limit is equal to 1. Okay, so there's a unit power signal, e raised by j omega naught t. Okay, here's a small bit of an exercise that you may have done in the homework. So x of t is, let's say, cosine omega naught t, right? The energy in this signal is clearly, you can show that this is infinity, right? So it approaches infinity because it's a never-ending signal. You take the square and the area under the curve is always going to be, so it keeps on increasing. That's why it's infinity. But what about the power? So if I were to compute the power on this, is just a small exercise. So this is minus t to t cosine squared omega naught t dt. This is equal to limit t going to infinity 1 upon 2t. And I am going to use trigonometric identity here. Cosine squared theta is 1 upon cosine 2 theta. Okay? So therefore this is 1 upon cosine 2 omega naught t divided by 2t times dt. And this is equal to limit t going to infinity 1 upon 2t And this is, this integral is, sorry, 2t here, right? So this is 2t divided by 2 plus limit t going to infinity, 1 upon 4t, right? Integral from minus t to capital T, cosine to omega naught t dt, right? And I mean, you can go ahead and evaluate this integral if you want, but I know that this is equal to 0 in the limit, because what's inside the integral is finite, what's in the denominator becomes infinite, so therefore the division is equal to 0, and therefore this is equal to half, right? So there's something wrong there. This is here 2, right? So power signals, or sorry, periodic signals typically are power signals. Okay, so periodic signals are typically power signals, right? So if you compute the power in periodic signals, that's going to turn out to be finite, but the energy is going to be infinite. The reason why the energy is going to be infinite, because they never end. I mean, they go on always. Okay. Okay. I just want to quickly talk about and give you a demo as well of general complex signals. So this is, I mean, we're not going to be using this too much. I mean, circuits में हम ज़्यादा इस्तेमाल करते हैं. But here, so right, so general complex exponential signals. And this is the form that they take, right? So the form that they take is x of t equals e raised to power sigma plus j omega times t, right? So, I mean, there's a real part to the exponential, not just a complex part, right? So therefore, this is e raised to power sigma t times e raised to power j omega t, okay? So what do you, I mean, if I were to visualize this, I mean, what would this be? First off, is this a periodic signal? Is x of t periodic? Who has an answer to that? The answer is no. Okay. So can anybody else answer why the answer is no? Can anybody else explain why the answer is no? The Saad Raza? Saad Raza, are you there?
Yes, sir, but I'm not sure.
You're not sure. And who else is sure? Can you venture a guess, Saad? Why do you think it's periodic, or why do you think it's not periodic? So e raised to power alpha t, is that periodic? Right, Masna? Can you unmute yourself? You're right. Okay, you have the right answer. Right?
Yes, sir.
Because the signal decays, because the signal decays, so it cannot be periodic. Just like a decaying exponential is not periodic because it does not repeat itself. Similarly here, because of this part, if sigma is not 0, because of this part, this either decays or grows depending on what values of sigma is. Okay? So the answer is no. But if you were to plot this out, right? So x of t, what would look like is e raised to power sigma t cosine omega naught t. And once again, this is an application of Euler's identity. So this is j times e raised to power sigma t sine omega naught t. So therefore, this is now decaying sinusoid in the real domain and a decaying sinusoid in the imaginary domain. Okay? Or growing sinusoid in the real domain and the growing sinusoid in the exponential in the imaginary domain, depending on whether sigma is positive or negative. Okay? And in 3 dimensions, what would it look like? What do you think? 3 dimensions, remember this was a spiral. If sigma equals 0, this would have been a spiral, right? Agar sigma is not equal to 0, what it would be? Right, so Hamza says it's a spiral that is, which is getting closely wound. So growing or shrinking spiral, okay? So Hamza, आप जो कह रहे हैं मेरे ख्याल में you're referring to
So
frequency.
when sigma is negative, the spiral will become like shrink होता जाएगा वो, क्योंकि the diameter of each circle will decrease with each complete revolution.
When you say shrink, उसका क्या मतलब है? I think you mean shrinking in the amplitude domain, right?
Yes, sir.
Okay.
Yes, sir.
Let me show you. So it's just frequency of 4 pi. So I'm going to pull up the code here just so you can see what I'm doing. Right. So this is 4 pi. Right. So the frequency is 4 pi. Right. And let me change sigma to minus 0.2. Right. So I would expect that this is a decaying exponential. Right. So let me run this and show you what happens. So this is what it is. So it's once again a spiral, except that spiral is shrinking in amplitude as time goes on, right? So this is what's happening here. Okay, ऐसा spiral का amplitude कम होता जाएगा because sigma is negative, right? And ultimately it would die down, and that's the reason why it's not periodic, because of that sigma there. Okay, and similarly, if I have a sigma of, let's make this plus 0.2, and this is where you would expect this to be a growing spiral. Okay, so let's do this. So this is a growing spiral, right? So this is the time axis, this is the real axis, this is the imaginary axis, this is the real axis. Okay, and I can pull this around just to show you kya real domain mein kya hai. You see, this is so this is the sinusoid, okay, and which is growing in amplitude. And similarly, ऊपर से देखेंगे इसी तरह की चीज नजर आएगी, except the phase is going to be 90 degree off. अगर मैं सामने से देखूं, तो this is what it's going to look like, right? So I've collapsed the time dimension. The time dimension is actually coming out of the screen, and this is what the projection is on the imaginary axis of the real axis. So it's moving. So the frequency is ulti hui hai, sorry. The curve is imaginary axis, positive axis. Right. So yeah, you get the point, right? So right. So this is what it looks like. Okay. So this is still a spiral, but the circles are growing as a function of time. Okay. So this is where I will stop. Any questions that you may have? No questions? Okay. What I want to say, I had a couple of announcements.